All right, this is a little bit past the end of the last slide, but I figured I'd cover a little of this material again. Once again, this thing called spectroscopic parallax, it's really important to understand that it has absolutely nothing to do with parallax, right? The traditional using a baseline and measuring angles. It's really just using the HR diagram to and our knowledge of the HR diagram to figure out how far a star is away using absolute magnitude. All right, so that's really important. And then so we have to identify the spectral class, right? The O, B, A, F, G, K, M. Which class is it in? Of course, that has to do with temperature. And then we have to estimate the luminosity. And then we use the inverse square law. We're actually going to do some of this in lab. So you'll see some of this. All right. So again, within the solar system, out to maybe 1 or 2 astronomical units, we can use actual radar to bounce off things. In fact, one of the first ways to very accurately measure the distance to the sun was actually using Venus, because Venus undergoes phases. When Venus was half full, just like when the moon is half full, then there was a 90-degree angle between the Earth, Venus, and the sun, and then you measure the angle, bounce radar off of Venus, which radar will actually bounce off of Venus, and so you could very accurately measure the distance to Venus at that moment, that Venus, the Earth, and the Sun were at 90 degrees to each other, and then you use parallax, the good old traditional parallax. All right, so again, stellar parallax is seeing actual parallax in stars, so that works out to roughly 200 parsecs. Although, in the 1990s, we sent a spacecraft called Hipparchus to extend the baseline beyond 1 astronomical unit, which is what we traditionally used as the baseline. And then just a few years ago, within like 10 or 15 years ago, there was a spacecraft that the European Space Agency sent up called Gaia. And Gaia has extended the baseline so that we can actually go out using this stellar parallax out to pretty accurately out to about almost 10,000 parsecs. So that's actually important. And so this what we're able to do, and this is always desirable in any of the sciences, is you can use the information from Gaia. In this range here, where before we could only get out to stellar parallax distances, or spectroscopic parallax distances, and now we can directly measure using stellar parallax and using the information from Gaia, because Gaia's the baseline is so much larger. All right, let's see. So this is extended. So we discussed this. Now the thing is, with this, I think I mentioned this earlier, that we have to be able to distinguish between whether a star is on the main sequence, because or it's one of the giant stars, or even supergiant stars, like it's up here. All right, so this is what they call luminosity class, and basically, the way this works is for very broad spectral lines. So these are usually absorption lines. You can have let's say a K star, the example that they're using here. You can have a K star that is because of these very broad, wide. Absorption lines, that tells you that it's a luminosity class 5, And we use the Roman numeral 5 to see the V. And so anything that's a class 5 for luminosity class is on the main sequence. And so it's very important to understand that that's on the main sequence. These class 4s, we'll actually get into that a little bit later. And then, of course, there's class 3, class 2, and then there's class 1A and 1B. Those have very, very narrow absorption bands. And so we can distinguish. That's the main thing, is we can distinguish, just a given star. Let's say it happens to be a K star. It doesn't have to be K. Obviously, it could be a G star. But you can distinguish whether it's a G5 or, a G4 or a G3 and so forth, right? And so you know what part of the HR diagram it's on. Why is that important? Because when it's a main sequence star, in any of these spectral classes, remember these are spectral classes. These Roman numerals are luminosity classes. When you know the spectral class and the luminosity class, you can go over here and estimate what the luminosity is from the main, from this main sequence, right? You can just draw a straight line over to the luminosity. They have to be on the main sequence. These stars have to be on the main sequence for us to do this. But then once you can estimate the luminosity, the absolute, let me put it that way, that's really important. Once you can estimate the absolute luminosity, you can use this thing called spectroscopic parallax. That's just what it's called, to figure out the distance to that object. All right, so again, and that's something that we'll do in lab. You'll see the equations that we use to do that. All right, so here is some examples. Let's see. So extending the as it says, the cosmic distance scale. So we can tell the difference between giants and supergiants, and we can also tell whether something's on the main sequence. So of course, if we look at this is just a good example of, one spectral classification, right? This is a K-type star, and you can have many different K-type stars, right? So you can have like a K. And the spectral classes go from 0 to 9 as well. And then there's this Roman numeral. And so if it has the Roman numeral, and of course that has to do with the width of the absorption lines, you can tell, again, whether it's a main sequence star, a giant star, or even a supergiant star. All right, so that's how we can distinguish these things. Now, how do we know mass, right? How do we know the mass of objects? There are certain stars, so when we look in the night sky, you can actually see with a pretty moderate telescope. In fact, you can actually see binary stars, two stars that are orbiting around each other, and they're usually orbiting some center of mass. There's actually a really good visual binary that is in the constellation Ursa Major. It's actually it's one of the stars one of the 7 stars in the Big Dipper. And it's called Mizar, if I remember correctly. It's called Mizar. I'm pretty sure it's that one. Anyhow, that one you can actually tell it's a binary star even with a small pair of binoculars. This is another star. They're just using an example right here of where this star was at different points. And once you can see that the 2 stars are orbiting each other, you get orbital information, and you use this thing called Kepler's third law, which gives you mass, or it's really the modified version of Kepler's third law. Kepler used the law to determine the masses of the planets and the positions of the planets going around the sun. But we modify. In fact, Isaac Newton was the one who modified it to give us the masses. All right. So another thing that you can do with if you have binary stars is so this is actually a really good example. So if you take a look here and you have these spectral lines, right? So this is, some particular atom or molecule. It's probably some atom, and you could look up into to tell what the chemical composition of that star is. But another thing that can happen is when the two stars are orbiting each other, you can get the exact same pattern. But this is exactly what we mean before when we were talking about redshift and blue shift. So if something is redshifted, the same pattern moves over to the red end of the spectrum. So notice this, like this. Let me get my mouse here so you can see it. Come on, where's the mouse? There it is. All right. So in the laboratory, so at rest, you get this particular pattern. And then when we're looking at a star, you get the same pattern because you're talking about the same element. But notice it's shifted over to the left. In that particular case, it's redshifted. And then you can actually measure how much, the delta lambda of each of these. How much of the change in the wavelength is going on. And then, of course, when the star is if you look at this picture, like if the star is approaching us, that would be blue shifted. If the star is moving away from us, that's of course red shifted. And so astronomy, we look at these kind of things, and you can see this pattern, this reoccurring red shift, blue shift, and so you get orbital information from that. Remember, this is the Doppler effect, and so you can by knowing where these lines are supposed to be when an object is at rest and how much they've moved, you can tell how fast the object's moving. Now it's actually much more complicated than that because the stars are not always going around each other in a like this, like from our vantage point, they're not at right angles to from the way we look at them. They could be some oblique angle that you could, you don't know what the angle is necessarily. But there is, we actually can, there are people who work on this kind of thing. So you can kind of try to figure out what the angle is. But there's another way of doing that with what are called eclipsing binaries. Right? And this actually works very similar. And we knew about this long before we could detect planets around other stars, right? But this is the exact same method that we find what are called extrasolar planets around other stars. But in this case, it's two stars orbiting each other. I probably have mentioned this multiple times that in our galaxy, the majority of stars have a companion. In fact, our solar system is a little different. There are solar systems that just have one star, like ours, but the vast majority, more than 50% of the stars that we see out there, are in binary systems, and in some cases, trinary systems, or even more. So these are stars that orbit each other. Anyhow, when one star passes in front of the other from our vantage point, they just happen to line up from where we are in the galaxy, you can actually measure that. And so you can actually look, if you look at the intensity as one star goes behind the other, there is a decrease in intensity. And then, when the star appears on the other side, this intensity goes back up. And so we can measure how much time this takes, right? We're looking at the time. And so from that you can get how fast the orbit is taking place. You can even estimate, from the time it takes to go from the peak intensity to the lowest intensity, how large the star is. And of course the other star you can tell by this part of the curve. So these intensity versus time curves are very, very important. But that's for eclipsing binaries. That's actually kind of a rarity. But they're out there. There are many stars in our galaxy. I don't know, how can I describe it? It's not it's not common, but it's not completely uncommon either. You know,